Now we have touched on extracting information from standard form. We've talked about how to extract information from intercept and or vertex form. We now need to go into a little bit more detail about vertex form. Up until now, we haven't talked much about vertex form, but vertex form will show up, and it will be important to know what you're looking at when you look at vertex form, and again, what information you can extract from vertex form, which is reiterated here. So we have f of x equals a times x minus h squared plus k. Do keep in mind that f of x can also be thought of as a y. In terms of finding the zeros from vertex form, we actually talked about this a few pages ago. We talked about the fact that the way that we can extract the zeros, which remember are also the x-intercepts, they are also the value of x when y equals 0, and that indeed is one of the ways that we can extract the intercepts, x-intercepts, or zeros from vertex form. We can just set y equal to 0, so we set this side of the equation equal to 0, and then we just use typical equation solving algebra to solve for the value or values of x, and that is a hugely important point here when we go through this process of setting y or f of x equal to 0 and then solving for x. There is often going to be a step at which we have to account for the fact that when we have a squared variable, let's say we have n squared equals 16, and we square root both sides of this equation, we do have to account for the fact that n can have both the positive and negative value. N equals positive or negative 4, because both 4 squared and negative 4 squared will give us 16. That is how we find the zeros or x-intercepts. We set y equal to 0 and then solve for x. The values of x that we get are the zeros or x-intercepts. How do we find the y-intercept of the parabola? The same way that we would always find a y-intercept. We set x equal to 0 and then we solve for y or f of x. So again, we're just making this term here equal to 0 and then we solve for our y value. The orientation of the parabola, we figure out the orientation of the parabola in vertex form exactly the same way that we do it in standard form and intercept form. We just need to know that when a is greater than 0, in other words, when a is positive, we have a opening upward or smiley face orientation, and the vertex is a minimum. When a is less than 0, in other words, when a is negative, we have an opening downward or sad face, a frowning parabola, and the vertex is a maximum. The x-coordinate of the vertex. So these two here are the most, I would say, significant ones when it comes to vertex form, the x and the y-coordinate of the vertex, because the vertex, and actually I should include all three of these all sort of go together. The vertex form makes abundantly clear what our coordinates are at the vertex, because the h and the k, in other words, whatever is in those two positions, the h position and the k position, are the coordinates of the vertex. That is why vertex form is called vertex form, because vertex form makes clear or lays bare the x and y coordinates of the vertex. So basically, if we're looking at something in pure vertex form, all we need to do is find out what is in the h position and what is in the k position, h position and k position, and we will know where our vertex is. Now keep in mind that when it comes to all functions, when we're talking about the value of the function, we are talking about the y value. If we're talking about the maximum or minimum value of a function, we're talking about the maximum or minimum y coordinate. Well, when it comes to a parabola that is down facing or frowning, then whatever the y value is at that maximum point, which we know if we're looking at vertex form, the y value is going to be k, then the parabola's maximum value will be k. It will be whatever value is in this position, and if the parabola is the more quote-unquote normal parabola that is opening upwards, in other words, when a is positive, then whatever the value of k is at that minimum point, at that vertex minimum, we know that is the minimum value of the function. So again, to recap, h comma k are the coordinates of the vertex. Whatever's in this position, whatever's in this position, those are the coordinates of the vertex. And we know that that k there is going to be the maximum or minimum value of the function. In this case, the function is f. That is how we extract information from vertex form. Let's take a look at example 31 here at the bottom, using vertex form to determine the vertex, which is the main thing that vertex form is good for. So what we're going to do here is we've got a bunch of parabolas, a bunch of quadratics. Some of them are in pure vertex form. Some of them will need to be rearranged into vertex form. We'll see how to do that in a moment. And we just need to know the coordinates of the vertex, and then we need to know whether that vertex is a maximum or minimum, and using the information in the table that we just ran through, we'll be able to do this hopefully fairly simply. So 31a, this is the equation that is already in pure vertex form. We should be able to see that the 3 is in the h position and the 4 is in the k position. So we know that the vertex here is going to be 3, 4. Now whether that vertex is a maximum or minimum, remember that will have to do with the a value. Here the a value is positive 2, and when an a value is positive, it means the parabola is oriented in the opening upward orientation, and therefore this vertex will be a, not a maximum, a minimum. This vertex will be a minimum. In example 31b, by the way, if you want to run through the rest of these on your own and then come back and join us, that might not be a bad idea. In 31b, I am going to do a little bit of rearranging here. I am going to first of all subtract this 5 from both sides of the equation. I am then going to also rewrite that x plus 2 as x minus negative 2, and then I'm going to add the negative 5 over here. Minus 5 is the same as plus negative 5. So now that I have my equation in pure vertex form, I should be able to see that my h is the negative 2 and my k is the negative 5. Keep in mind, this is one of those cases where if you see something like x plus 2 squared and then some other stuff, you also could just think about this as taking the opposite of whatever number is here. So if you have x plus 2, you're just talking about x minus 2, which in effect does the same thing that I just did here. That's perfectly fine if you want to think about finding the x coordinate of the vertex in that way. So I know that my vertex here is going to be negative 2, negative 5. Those are my h and k values. And because a here is negative 1, a is negative, a is less than 0. Remember that when a is less than 0, we have a downward facing or frowning parabola, and we know that our vertex is going to be a maximum. In the case of example C here, so what I'm going to do is this. I'm going to expand this out a little bit, and I'm going to write negative x minus 0 squared. X minus 0 squared is no different from x squared, and then we are adding to that 0, right? There's no number out here, so really in effect what we're doing is we're adding a 0. So I can see that my h and my k both are zeros. So my vertex here is going to be the origin. It's going to be 0, 0. H value, k value, and because once again we have a negative a value, we know that our vertex is going to be a maximum. Again, this parabola will be oriented downward facing, and the vertex of that parabola will be right there at the origin. In example D here, don't get freaked out by the fact that we don't have numbers in the h and the k position. That's okay. It doesn't matter what occupies those positions as long as we can identify what occupies those positions. So we can do this either by taking the opposite of this term, so that's negative n, and then this term here, that's 2m. So those are our h and k values. Again, you could also rewrite what's in parentheses as x minus negative n so that you can see that the negative n is in the h position. And we have a positive 1 in the a position, so the parabola will be opening upward, smiley face, and we will have a minimum. So our vertex here will be negative n, 2m, and that vertex will be a minimum. What we have on the next page, we're going to talk a little bit about models, minimums, and maximums. We will see questions that involve models, quadratic models, linear models on this test. All we're talking about when we talk about models is we're using some equation, some functions equation to model some real life behavior. So in this case, we have the height of a ball after release, and that height can be modeled by a quadratic function. So when we see something like this, so first of all, let's talk about what we're seeing here. We are seeing a quadratic in standard form, right? That is ax squared plus bx plus c. Our a is negative 4.9, the b is 40, the c is 1.5. Of course, we do have a t here instead of an x. Why is that? Well, it's because we are measuring the height of the ball in terms of the time after release. So instead of using an x here, we are using a t here to indicate time. And what we see is that the ball is released, the ball starts climbing, right? Its height starts going up and up and up and up and up until a certain point at which, and that point is 4.1 seconds after we release the ball, we get to a height of 83.1 meters. That would be our maximum height. The 4.1 seconds would be the time at which we reach that maximum, and then we start falling from there. The height of the ball starts decreasing. Now, in terms of the coordinates of the vertex, well, we just talked about what those values mean. The x-coordinate, that 4.1 seconds, that is the time after release that we reach our maximum height, and that maximum height, of course, is the 83.1 meters. So that is the maximum height. It is also, I'm going to jot this down up here, the maximum value of our function of h, or h of t, whatever you want to call it. So that is the maximum value of h. The maximum value of h is analogous to the maximum height. Now, we are going to now look at this equation in vertex form. If you are understanding this, it shouldn't be a big surprise that 4.1 seconds will occupy this h position, right? That is the x value. I know it's a little bit confusing here because the h here and the h here can seem to be the same thing. They're not. Remember that this h is simply the h from vertex form, and this h happens to be the name of our function in this case because our function measures height. So this h here and this h here, do not confuse those. This h is actually a t value. That is actually a time value. And again, in that h position, which is the x coordinate, or in this case t coordinate at the vertex, we have a 4.1. Why? Because the vertex has an x coordinate of 4.1. And then, of course, that k position, which is the y coordinate, or in this case, h coordinate at the vertex, we are going to have 83.1. That is the maximum value of this function, and that is the y coordinate at the vertex, which is a maximum. So our vertex is at 4.1 seconds and 83.1 meters. So the maximum value of this function and that y coordinate, I'm going to go ahead and highlight this. That y coordinate at the parabola's vertex is synonymous with the function's maximum or minimum value, in this case with the maximum height that the ball reaches. You may see a question like example 32 that asks you to look at a quadratic model and determine what the maximum value of the function is, or even what the x value is that produces the maximum value of the function. In example 32, obviously pause the video if you want to try this on your own. If we're given a quadratic function in vertex form, finding the maximum or minimum value of the function should be very simple because, as we spoke about before, the k value is the maximum or minimum value of the function. So in example 32, we have a shoe store determines that its monthly revenue R in dollars is given by the function R of P equals whatever, where P is the number of pairs of shoes sold each month. What is the store's maximum monthly revenue? Okay, so if we take a look at this, we can see that we have a negative a value. So that does mean that our function is going to be frowning and we are going to have a maximum. Our vertex will be a maximum. That vertex does occur at 140. There's our h value. and there's our K value. So 140, comma, 6,300. Well, remember, they told us that the P values here, which are like our X values, right? There's our input, which is like our X. Our P values are a number of pairs of shoes. So that's 140 pairs of shoes. And R, which is like the Y value, R is the revenue in dollars. So that 6,300 is a number of dollars, and it happens to be the maximum number of dollars of revenue, which means the answer to this question, very simply, is just that $6,300. And again, as I said a couple times already, whatever's in that K position there is always going to be the maximum value of whatever your function is. In this case, it's the revenue. So $6,300 will be our maximum monthly revenue reached when we sell 140 pairs of shoes. Down at the bottom, example 33, let's go ahead and read through this. Manufacturer models its daily production cost C in dollars with the function C of U equals whatever, where U is the number of units it produces per day. If the manufacturer wants to minimize its daily production cost, how many units per day should it produce, and what will be the daily production cost? So how many units to minimize cost, and what will be the daily production cost? So we have to do two things here. We have to find out how many units we have to produce in order to minimize the cost, and what will be that minimized cost. Now notice in this case, what do we have? We have a standard form quadratic. In a previous part of this section, we talked about the fact that converting standard form to vertex form would involve completing the square, but I also said at that time that we generally are not going to need to know how to do that, and that is because we talked about how to find the vertex from standard form. And the way that we can do that is by using what we learned about finding the x coordinate of the vertex. So we can actually find our h value, right? We need h comma k. We can find that h value by doing negative b over 2a. We learned this when we talked about extracting information from standard form. And in this case, negative b over 2a is going to be negative 40, right? That's our b value there. In fact, we should write down a equals 1, b equals negative 40, and c equals 800. So we have negative 40 over 2a, which is just 1. So these guys turn positive. We have 40 over 2, which means the x coordinate at the vertex here will be, and again, this parabola is actually going to be oriented facing, opening up, smiley face. We know that because our a value is a positive 1. So we will have a minimum as our vertex. So we know that the x coordinate there is 20. And now all we need to do to find the y coordinate there, which will be the minimum value of the function being the daily production cost. So whatever this value is here will be the minimum production cost. So all we have to do now is take that 20, which is in this case a u value, u and x are synonymous here. All we have to do is take that 20, plug the 20 into our function. In other words, we just have to evaluate the function at 20. Now we have to do this without a calculator. Hopefully this will not be too difficult. No, it looks like these are all multiples of 10, so it looks like this shouldn't be too bad. 20 squared, we should be able to do that in one of a few ways. One way is to just know that 20 squared is 400, or we could write this all out. We could write it out longhand, 20 by 20. We could also just do 2 by 2 and then add in the 2 zeros. 2 by 2 is 4. Adding in the 2 zeros, we get 400. So there are multiple ways to figure out how to do 20 squared. So it's 400. 40 times 20, again, that's 4 times 2, and then 2 zeros, so that's 8, and 2 zeros, so that's minus 800 plus 800. That works out nicely. Minus 800 plus 800, they go away, and we get 400. So what this looks like is that when we produce 20 units, we will have our minimum daily production cost of $400. So those are the two answers to the question. We have to produce 20 units, and the production cost will be $400. So again, is there a need to convert to vertex form here to find the minimum value of this function, to find the number of units that produces that minimum? No, we can use what we learned from standard form in order to find the x coordinate, in this case u coordinate, at the vertex, plug that u coordinate back in, and find the corresponding c value, find the corresponding daily production cost value. At the top of the next page, we are going to go into something that we will talk about at another point in the manual, this idea of translations or shifts of a graph, but we want to talk about this here mostly because when it comes to vertex form, it is important to be able to see how vertex form of a quadratic will relate to some of this translating or shifting. So first of all, what is translation? Well, translation is just shifting. We're just shifting every point on a figure, an entire graph, the same distance and in the same direction. So translation, shifting or sliding, every point, same distance, same direction. So we can see in this figure over here, we have taken triangle ABC, and we have shifted points A, B, and C, along with all of the points along the sides of this triangle, down 4 and to the right 3, and we have ended up with the image of, you might see that term, the image of that, that's just the result of the translation, the image of ABC, so A prime, B prime, C prime over here. So A prime, B prime, C prime is what we would get if we took triangle ABC and shifted triangle ABC down 4 and to the right 3. Only the locations of the points changed. Everything else is the same. The angle measures, the side lengths, the orientation. We have not rotated the triangle. We have not stretched or compressed the triangle. Everything else is the same. All we did is move the triangle. That's what a translation is. Now, when it comes to a parabola, let's take a look at how the regular old y equals x squared parabola, which has its vertex at 0, 0, we can see that here on the graph, which has its vertex at 0, 0. Let's see how that parabola relates to its translation, or to a translation of it, 4 units to the right and 2 units up. So you can see we've gone 1, 2, 3, 4 units right, 1, 2 units up, and we have ended up here where now our vertex, which was at 0, 0, ends up at 4, 2. Well, we know that if all we did was move this parabola, we didn't stretch it or compress it or flip it or anything like that, we just moved it, that means that all points went 4 to the right and 2 up. Of course, we can see that in the vertex here, and we can see that in vertex form, instead of y equals x squared, we now have y equals x minus 4 squared plus 2. Well, we can see that that 4, that corresponds to the horizontal shift. And that 2 corresponds to the vertical shift. The point is that in vertex form, not only do the h and the k values give us the coordinates of the vertex, they also tell us where we have shifted our parabola from the regular old y equals x squared parabola, or even from other parabolas that aren't vertexed at the origin. So let's summarize these relationship, the relationship between vertex form and translation. So first of all, if we add or subtract a number directly to our y or f of x, in other words, if we take f of x and we add a certain value, in this case k, to it, or subtract a certain value k from it, what we get is we get a vertical, that does not spell vertical, vertical shift. We'll just call it a shift, although that's synonymous with translation. And if we are adding a value, we are going up k units. And if we are subtracting a value, we are going down k units. So we go from having an xy coordinate to having an x comma y plus k coordinate. In other words, we have to add that k to all of our y coordinates, and if we are subtracting the k, we go from xy to x comma y minus k. So again, the k here shifts the graph up or down. If k is positive, we go up. If k is negative, we go down. Now, if we add or subtract directly to x, in other words, if we put our number that we are adding or subtracting with the x inside the parentheses, you notice how this number up here is outside the parentheses, then what we are going to do is we are going to horizontally shift. So I'm going to write horizontal shift here. And if we add a number to x, we are actually going to shift. This one's a little bit confusing. I didn't write shift up there, but that's okay. We are going to shift left h units. And if we subtract a number from x, we are going to shift right h units. Now, the explanation as to why the plus goes left and the minus goes right, it's actually not that difficult to understand why that happens. We are not going to go over that in this video here. I would, for the purposes of the SAT, I really would just have this memorized. So what do we do over here? We go x minus h comma y and x plus h comma y. So again, the x minus h in parentheses, okay, if in the function we are subtracting a number from x, that actually means that all of our x coordinates increase by that h. Again, I know it's confusing. I would try to memorize this, and certainly if you are the type of student that needs to understand why this stuff happens, make sure you seek clarification from your tutor or from additional resources. These rules apply to all functions, not just to quadratics. Let's take a look at example 34, which does not specify that we are dealing with a quadratic, but again, that does not matter. So on the xy plane, the graph of y equals f of x contains point A with coordinates 2, -1. What are the coordinates of the corresponding point on this new function? So we're going from f of x that has the point 2, -1 on it to f of x plus 3 minus 2. Hopefully this should be easy enough that you can look back at all of the information up here and say, okay, that's not all that complicated. Remember what we said. If we are adding a number to x in parentheses, then we are actually shifting left. So this is going to shift left 3 units, and minus 2, so we are subtracting a 2 from our f of x. We are subtracting a 2. Well, that means we're going to go down 2. So if we are at 2, an x value of 2, and we shift left 3 units, we end up at -1. And if we are at -1 and we shift down 2 units, we are at -3. So the corresponding point will be -1, -3, -1, -3 on the new function. So we have this new function. Everything has shifted left 3 and down 2, which means this point, 2, -1, will now be at -1, -3. Let's try another example. But before we get there, I just want to reiterate a point I've already made. You may see some terminology or some notation on these questions that we've already kind of gone over and we've already mentioned. You might see something like this, x, y, and then this arrow between them to x minus 3, y minus 2. All this means is that an xy point has shifted down left 3 and down 2, which is actually exactly what happened here. Left 3, down 2. So we could indicate that left 3, down 2 shift by saying that our xy coordinates are going to go to x minus 3, y minus 2. We're taking 3 away from all of our x coordinates and 2 away from all of our y coordinates. We also might see the term image. Image just means the result of a translated figure. So again, at the top of this page, we saw triangle ABC shift down 4, right 3, and become this new triangle. Well, this new triangle and all the points on it would be the image of the original triangle. At the top of the next page, example 35. Let's go ahead and read through this. If you want to try it on your own, pause the video and try it out. The figure above shows point A on the graph of f of x and its image A prime on the graph of g of x. Okay, fine. So what do we have? We have f of x here, the black one, and then we have g of x there, the gray one. Fine. If g of x equals f of x minus m plus n, what is the sum? We need the sum of m and n. Okay, so let's take a look at this. We've got g of x and we've got f of x. How are they related? Well, f of x has been shifted. So let's look at this point right here and this point right here. So a has been shifted to get its image left 3 and up. How many is that? That's 1, 2, 3, 4, 5. So left 3, I'm going to write those down. Left 3, up 5. We can see that on the graph. We can also see it in the points themselves, right? If we go from 0, -5 to -3, 0, well, again, that means we went left 3 and we went up 5. So left 3, up 5. So what does that mean about the relationship between the actual functions? It means that g of x, in order to get g of x, we would have to take the f of x function and we would have to do f of, if we want to go left 3, we need to do plus 3, right? F of x plus 3 will shift the graph of f of x left 3 units. And then if we want to go up 5, if we want to shift the graph of f of x up 5, we have to add 5 to f of x. So it looks as if, again, in order to get g of x, in order to get all of the points on f of x to shift left 3 and up 5 to get to g of x, we have to add a 3 to the x in the f of x function. That will shift left 3. And we have to add a 5 that will shift up 5. So it appears that n is definitely 5. That's the easy one. So n equals 5. To get m, we might want to reimagine x plus 3 as x minus -3. And then we can sort of just match up the m and the -3. So m is going to be -3. They want the sum of those two values. 5 plus -3 is 2. I understand that for some students that can be a little bit confusing. Translation questions can be a little bit confusing. There will be plenty of these questions for practice, so you will get some sense of how they work and you will get more familiar with them. But for right now, and as I mentioned before, we do go over translations and how certain changes to the function of a graph will affect how the graph looks on an actual XY coordinate plane. So you will have more exposure to this concept. You will become more familiar with it.